All right, so we have first regular talk of F#Conf, which will be on concurrent programming with F#, and the talk is from Tamish Vendan, who is joining us all the way from India. Tamish, hello, welcome.
Thanks, Thomas.
All right,
good morning, everyone, wherever you are.
Let me maximize this window. How do I do full screen in Skype? Ha ha ha. Show full size video. Well, I'll figure it out as we go. So Tamish, what time is it? Where are you actually calling us from?
I'm calling from Chennai, India. It's 9:30 p.m. over here.
All right, 9:30. So it's already pretty dark, right?
Yes.
That's why the video is a bit blurry. But we'll switch to some technical content pretty soon. Have you been watching the previous F#Conf when it was happening 2 years ago?
I was actually, just getting started in F# during that time. So it was quite a, a kind of good journey, which I can, remember for a very long time, speaking in an F# conference after 2 years.
Wow.
It's a privilege.
That's a pretty quick start. And you'll be talking about concurrent programming, and we'll see the Hopac library. So that's some pretty advanced technical F# stuff as well. All right. So I'll switch to your slides, and if you can turn off your camera, I'll turn off my camera as well, and then you can get started. I think turn off your camera, but give us the slides. Good.
Yeah.
And I think we're ready to go. All right. Let's get started. The screen's yours. Thank you.
Thank you, Thomas. Thanks, everyone, for tuning in for my talk, Concurrent Programming with F#. Myself, Tamil Vendan. I work as a lead consultant in a startup called Agita. And I blog at demystifyfp.com, and you can find me on my Twitter, which is on there on the left side of the slides. Okay, let me start with what is concurrent programming and how it can help us through an example from a real world, use case. I was once asked to build a GitHub profile API where we need to show the user profile along with his top 3 repositories. And when we are showing the repository, we also need to show the number of stars it has received and along with the languages that it has been used inside that repositories. So this is the standard requirement that I got when I was working in an F# project. So basically, in order to fetch this information from GitHub offers 3 different APIs. To fetch the user information, there is an API called user/username in the api.github.com, where if we call, it will give us the user profile information. And if you want to fetch the repositories, we can call the repos API, and that will give us all the repositories of the user. And for the sake of simplicity, I'm not going to talk about the pagination here. I'm just considering that given a repo, it will give you the initial set of repositories of the users. And another thing is, if you want to fetch the languages that has been used inside that language, the repositories, we need to call another API by providing the username along with the repository name. So these are all the APIs that we need to call to fetch all this information in order to show in a single screen. Okay, let's talk about in a sequential world, how do we perform? We call the user API first, and then we call the repo API, and then we call the languages API for those top 3 repositories. And as time goes by, we will get a JSON response which has all this information intact, and we send that to the front end. So that's what a typical sequential world look like. Okay, let me introduce another world where I call the C world, where we have the liberty and we have the power to choose things and how we can execute things in real time. For example, if you look at in the previous example, there is no dependencies between the user API call and the repo API call. So ideally, we can make two things parallel, and we can leverage some the programming through the programming model. We can put these 2 things together so that we can get the responses of those 2 APIs in a shorter period of time. And once we got those 2 responses, now we know what are the top 3 repositories of the given user, and then we can call the languages APIs parallelly and get all the responses, and we can merge them together. And if you look at from the time perspective, there is a huge advantage over here. The earlier call, let's assume that every call takes a second to give the response. In the previous sequential world, where we are actually getting the response after 5 seconds. Whereas over here, since we have the things structured in such a way that we can leverage the parallelism, we are getting the same response in a much shorter period of time, say 2 to 3 minutes, 2 to 3 seconds of time. So that's the power of shuffling things together and running them parallelly, and we can get the power of concurrency, and we can get things in a much lesser time. So that actually leads me to the definition of concurrent programming. Now we saw what concurrency brings to the table, and one of my favorite definition of concurrent programming is actually from the talk called "Concurrency is Not Parallelism" by Hopac, where he defines something like a concurrency provides a way to structure a solution to a problem that may be parallelizable. See, parallelization is not the end goal of concurrency. The concurrency is all about how do you structure the things together, which eventually end up doing the things parallelly. And if you look at the previous example, there is not one way that we can structure the solution. This is one way of structuring the solution. We called the user and repo API parallelly, and then we called all the language APIs parallelly. Whereas in the case of other things, we may batch up the language APIs calls. Say, for example, we can batch only 2 API calls, and once it is done, we can call. So it's all about how do you structure the things together. And once you structure the 2 things together, like you just throw it up to the environment, and the environment takes care of running these things according to the structure that you have given to that. And that actually there is another definition of concurrency. It's all about composition of independently executing computations. All right. So if you look at these 2 definitions from a different perspective, it sounds much like a functional programming. What we do in functional programming, we do structuring the solution based on small functions, and once we're done with all those functions, we just compose them together and we provide the solution. So the concurrency functional programming, it's actually a good pass if you work on them together, and it gives you a nice set of abstractions, and using that abstraction we can build things which can be very hard to written in a typical object-oriented or in a procedural world. Okay, so let's see the things from the functions perspective. We have a user API call. How do we implement it? We write an API or a function which takes the username and returns the user. And if you want to implement the repo API call, we write another function which takes the username and returns a list of repositories. If you want to get the top 3 repositories, again, that is a function that takes a list of repositories and returns the top 3 repositories of the user. And finally, if you want to model the language API call, we write another function which takes the username and the repo name and returns the list of languages. So that's what we do in functional programming. We write functions, and that function in turn models the behaviors in the system. And once we write the functions together, the next thing is compose the functions together. I'm just showing you a function which takes the username and gets the profile which is the profile that we want at the end of the response. So over here, we are getting the username. We are getting the username as a function parameter, and once we got the username, we are calling the get user function, get the users. We are calling the get user repos, calling the user repos, and then once we have the user repos in place, we call the top 3 repos, and which will fetch us the top 3 repos. And once we have the top 3 repos, we just call the languages APIs with those input parameters, and it is feed us that's a plain forward, hello world kind of example for the functional programming. Okay, now things looks pretty straightforward in the sequential world. No complexity, nothing. We are not mutating anything. Plain simple stuff. Okay, how do we make it concurrent? Well, the functions in the concurrent world will have the similar signature, but the only difference is instead of returning something as it is, we put them into some sort of a context. And I don't want to use any word, and I'm just using the word C here, just meaning that it is a context. When it gets executed, it is going to give you the value. Okay. Likewise, for the remaining functions, we can say put those contexts in picture. Say in the username, just take of C and returns a repo of list. And likewise, for the languages API also, we can say things like, so we can get the username, get the repo name, and return the language list and put that into a context. And this context is actually what I mean is the C world, where now we have the value in some sort of a context. Now we can wrap around that, and we can provide some sort of a computation expression on top of that world, and using that we can now shuffle things together. For example, over here in the get username and get user repos, we know that it can be parallelizable. So what we are actually doing here, I'm using a infix operator over here, just that takes two different contexts and run them parallelly and give the responses back. And if you look at below, we have something called concollect. Again, we will touch that back in a little later. So it is something like, given a list of something in the C world, it runs all of them parallelly and gives you the responses. If you look at from the sequential version and the concurrent version, the only difference is those things which are highlighted. The rest of the things is remaining intact. And that's the beautiful thing of functional programming. We achieved a lot, but with respect to the code, we have written only very few things, which is something which got me into functional programming. And that's the only reason I'm actually, more into this kind of, what we are actually doing over here is small things added to the existing stuff, and it becomes very powerful. Okay, so what is this C world? Enough buzz around C and other things, but basically it's all about a programming model that enables concurrency. In F#, we can do concurrency through using 3 different programming models at this time. And one is the task of T, whereas it is coming from the .NET framework. I guess you guys might be very familiar with this one. And async of T is another programming model coming from the F# core library. And the last one is actually coming from a library called Hopac, which is providing an abstraction called job. Okay, and all these 3 programming models has a difference in their way of approaching concurrency. And due to the short nature of this talk, I'm not going to get into the different details of what each brings to the table and what is the differences among them. So if you are interested in dive deep into the differences, I recommend those 2 blog posts in the links. If you go through that, you will get an idea about what is the programming model of these 2 things. All right, so let's jump in, and in the rest of the talk, we are going to see what is Hopac library is all about, and using the Hopac library, how can we write concurrent programming with less code. All right, so what is Hopac library? Hopac is an F# library, and it actually brings in a programming model inspired by concurrent ML, a programming language from long back. Okay, this is in turn actually, if you are aware of something called communicating sequential processing, that actually inspired concurrent ML, and this programming model is inspired from concurrent ML. So this Hopac library actually brings in 3 different abstractions, and one of the important abstraction which we use a lot when we are actually working with Hopac is job. Job is nothing but a lightweight thread. You can spin up much like thread, where we don't have the luxury of creating a lot of threads inside a program, whereas in the case of job, it's a very lightweight. At the end of the day, it's just a .NET object. So you can create n number, you can even run millions of jobs inside a single machine and without any additional overhead. And then second abstraction that Hopac library has is something called channels. Channels is the way through which we communicate across 2 jobs. And there is another beautiful abstraction called alt, which we will be seeing in action in a moment. This alt is actually coordinates and communicates between the jobs and the channels. All right. So if you guys are already familiar with some Golang's concurrency model and Clojure's core.async, this is a pretty similar business, programming model. We will. This is something, but what actually F# brings here is all about how you are arranging things and how it can be naturally extending with respect to the functional programming. All right. So as with the tradition, let's start with the hello world. So this is how a hello world looks in the Hopac world. So what we are actually, we are creating a job which takes some time, a delay of 2000 milliseconds, and after it prints the hello world. Nothing fancy, just a job, and the Hopac library comes up with async, a computation expression called job. If you are something very familiar with async, it is exactly the same, but the underlying programming model is different. Okay, so if you execute this in an F# interactive with the time settings on, you can see the hello world in the interactive, and it took 2 seconds to print it. Nothing fancy, just plain simple hello world. What we are actually doing is we are simulating a job which takes some time to execute. All right. So that's enough for the hello world. I guess you will be might be more interested in beyond the hello world example. So let me show something from my use case. I was working in a product where we were dealing with a lot of microservices, and we are fetching the details from there and there, and we wanted to merge those data and send the result back to the client. So one of such requirement was we had something called a product service, which is giving the data of a product. And there is another service we had, which is giving the review of, which is storing the reviews of a product, and which is giving the reviews of the product back. And what we actually wanted was kind of a table join where we wanted to join the products with the reviews, and we want to return the results back. But the only thing is we cannot do joins. So now it is do different cloud services. So what we need to do is they need to make some two HTTP calls and get the results and combine them and return it back. So in order to do that, let's simulate this example over here. So I'm just putting that in the form of a function that takes a product ID as its input and returns a job. When it gets executed, it is going to give you the product of. I'm just making everything simple over here just to for the sake of example. So I'm just simulating a delay in the place of an HTTP in the place of an HTTP API call. And to get the product reviews, again, similar kind of function. It takes the product ID and returns the reviews. And again, I'm simulating a delay here. It takes some 3 seconds to return the response back. So coming back to the actual place where we are actually joining the results of two API calls and returning it back. This is the typical a code base which takes those two things together and put the data back into some sort of a structure and returning it back. That is, it takes a product ID and returns the product with the reviews. So this is something we are not doing any parallelism here. Like we're just putting things together and in a sequential order, and we are getting the things done. And if you want to make, if you run this in F# Interactive with the timing settings on, we can see that it gives the response after 5 seconds. The reason being we are just executing those two things sequentially over here. One takes 2 seconds and another one is taking 3 seconds. And coming back to the actual example of where we are going to introduce the concurrency here, it is using that infix operator. And this infix operator takes two jobs. If you look at from the previous example, that get product of ID returns a job of products, and the get product reviews of ID returns the job of product reviews. So what we are actually doing here, we are just telling the Hopac library, hey, we want these two things get executed parallelly and give me the results back. So this infix operator takes two jobs and return us another job, which is nothing but a tuple of the first and second jobs. And once we got the results back, we're just going to mesh the things together and we are going to return it back. And that's with just by introducing a single operator, we just made the things faster. And if we execute this particular function in F# Interactive, what we will get as the response in 3 seconds. That means the number of seconds that the longer operation takes. And we in the overall response time we saved 2 minutes. And this is an example from my personal experience. And this is something once we got these things together and we get all those things served. All right. So now we have something called GitHub Profile API that we saw in the previous example. In the previous example, we have something called 5 API calls. And what we have did over there, like we just get those two things together by using the infix operator. And once we got the infix operator, then using the something called job.concollect, which takes a list of jobs and asks the Hopac to run them parallelly. And once it got the responses, we are just getting those things together and we are returning it this back. So this is GitHub response profile API that we saw in the previous example using the GitHub, using the Hopac library. And once we got around that with multiple jobs, the next thing that we are interested in, how do we communicate with each other? In typical threading environment, we do something called inter-thread communication. In inter-thread communication, what we are actually doing is we will use some sort of logs, semaphores, and we use something like concurrent thread safe data structures, and using that we actually try to maneuver things together and we come out able to deliver the solution. But one of the most tidy thing about inter-thread communication is it is very hard to get it right, and even if you're getting it right, it is very hard to maintain in the long run, and eventually it will lead to something like it will be a maintenance nightmare, and we need to keep track of a lot of moving parts and other things. So one of the programming model that suggests how to overcome this particular way of doing inter-thread communication is communicating by sharing memory. And in the previous approach in threading based environment, what we are actually doing is we communicate by putting into some sort of memory, and we lock that things and we protect it, and then we enable those to develop to threads to make it shareable. But here in the case of Hopac, what we are actually going to do is we are just going to communicate from one place to the other place through some sort of a transport medium, and using that medium we are going to share the memory. All right. So that particular abstraction is called channel and alt. And these are nothing but abstractions from the Hopac library to communicate and coordinate between jobs. And they are actually synchronous by default, and it can be, it can be extended to support asynchronous as well. And it is extremely lightweight. It is first class. That means you can pass the channel around, you can get those things in place. And one of the most beautiful thing that we can get out of it is selective. Say for example, if you want to multiplex the things, and if you want to fan in and fan out, those things are much easier to do with respect to this abstraction. Okay, coming back to the examples that we are seeing so far, let's assume that we have another job where we have a list of jobs. Each job takes different times, and once it is completed, we want to print the status. This is the use case that we are going to solve. And in this example, if you look at here, if we execute this particular program in an F-Sharp Interactive, the outcome that we are expecting is if job 1 takes 1 second and job 2 takes 2 seconds, likewise job 3 and job 4 is taking respective times, and we want to print its status on the console. It's a very simple program. It's just going to keep track of when a job started and when it is completed. Okay, and in order to do these things, what we actually need is 4 jobs, which is simulating those 4 jobs, and there is one print job which is going to sit on the other end, going to receive those status of the job and printing it. So this is how it works. There is something called channel, and the channel can take any, it's a generic thing, it can take any data, and the job which is going to give the status is going to come into the channel and going to fetch the value, and it is a synchronous communication. The consumer also has to be in the channel to receive the value, and he will be taking that to take. And for the example that we are talking about, we are going to use something called job status, which is just communicating the started and completed of the job ID. Okay, so before getting into the code, let's see how it turns out in a virtual world. So it's like job 2 gets started first, and it gives its status to the print job. But at the same time, job 1 also has to be started. It is waiting in the pipeline since the print job is not available now. Once print job done with printing the job 2 status, it is going to pick the job 1 and print it. Once that is done, meanwhile, job 4 and job 3 has been started, and the print job after done with job 1, it is going to pick the message from job 4 and going to print it, and job 3 it takes the same thing for the job 3 and it's printing its status. So that is with respect to starting status. Completion, we have the liberty now, since all the jobs are going to complete in different time span. So the job 1, job 2, job 3 giving its status to the print job, and print job just printing it. So that's how in the virtual world. So let's come back to the reality where we are actually going to implement this in code, where I'm just going to write a function where it is nothing but it takes a status channel and an ID, which is nothing but the IDs of the job, and the delay which simulate how long the job is going to take. So when the job actually starts, we are actually giving the status to the job status channel, and after that we are just going to delay to simulate that some meaningful job is happening, and once that is done, we are just giving the status completed to the channel. So this is at the job to channel side of it. On the other side, we are having another job. We are just creating through another function called job status printer job, which takes the job status channel and takes the status from the channel and see whether the job status is started or completed, and printing is something accordingly. So it's a pretty simple stuff. And when it comes to orchestration, the main function, what actually going to put the things together is pretty simple. Like it just uniquely creates a channel and then creates a printer channel and printer job, and put all the jobs together in a list and run all the jobs parallelly. Now if you see here, all the jobs are executing in different time frame and sending their status to the printer, and the printer receives all those things together and printing it. Much powerful abstraction with less number of codes. And if you run the job right now, it will list down all these things in like this, and the overall execution time is just 4 seconds. And let's make this thing little complicated by introducing some delay to the printer. In the previous example, the job status printer just take the value and printed it. Now let's assume it is a slow consumer and it is taking some time to process it, And once it is, and I'm just simulating that through a delay over here, and once it is done, it just prints the status. So now if you run the example again, you can see the execution takes 7 seconds. In the previous one, it was just 4 seconds. Now it is 7 seconds. The reason being, now the consumer is slow. The producer is still producing in the same speed, but the consumer is lagging behind. And that's why we are having 7 seconds in the overall execution. So how do we scale it up? Just nothing, but we just add one more printer. Once we added a new printer, that puts that in the existing job list and asks everything to run together. Now, if you run this example again, it is faster again. So now we got back the 4 seconds back. So what we have seen over here is through jobs, we have run things parallelly, and through the channels we communicated between those jobs. And once we have communicated, we have find out that the consumer is taking some more time. We then scaled up the consumer with less number of code, and we got back this time again. So it is now 4 seconds. And what we saw in the previous example was synchronous, give and take. Hopac library offers something called bounded mailbox. If you want something like a mailbox kind of things like what we have in actor programming model, like if you want to have back pressure or some sort of mechanism where we want to be, we know that the consumer is slow, we can use something called bounded mailbox where we can define the queue length and we can make the producer and consumer work in tandem with some sort of a buffer. And there is another function called channel.send where we can send the messages without bothering about waiting on the other side. Okay, these are all the other modes where we can, using that, we can also solve this problem in another way. So that is channel for us. And that comes back to the last example of this talk, like is alt. Alt is nothing but a selective synchronization operation. We already have a list of channels, and those channels is pumping in different messages. And what if we wanted to choose among those channels? We need another mechanism, and that's what alt provides. So to see an example, let's see them in action. Okay, and we want to get an answer after some time. It's a plain simple thing. Again, a hello world kind of example where we know what is the answer is. The answer is 42, and we want to get the answers after some time. So we are having, I'm just simulating that behavior using something called get answer, and that takes a parameter to simulate the delay. And once the timeout happens, we are just returning the answer, which is 42. And if we run it now in the F# interactive, we can see it is responding the answer 42 after a second. And let's move on to this from this example, and we want an answer or a timeout. And this example where we are actually, we no longer want to find the answer within the particular time. We want to get the response saying that the user send me timeout. I don't tolerate with respect to the delay. So this is another function which is making use of the existing function. In addition to that, it is adding something called a new timeout, where it is receiving another parameter called tolerance. And what it is actually happening over here, it takes the tolerance as it's another delay, and inside the delay, it checks whether the timeout or the get answer, which one is first. And using choose, we are actually choosing between these two things, and whichever commits first, we are returning the results back. So if you look at the answer now, if with the get answer or timeout function with less time for delay and more time for tolerance, we can get the answer as 42. But if the tolerance level is little less than the lesser than the actual timeout, what we are actually going to see is the timeout as the response. And the reason being, the choose function is doing the synchronization between those two tasks for us. All right, so that is the alt for you. And the typical concurrent programming is always talk about fan in and fan out. Okay, it's all about how do we spread things together and how do we get these things together and they get return the result back. So in order to show that particular example, I'm going to show you another example from my personal experience where we have asked to calculate hash sum of all the files in a particular directory. So in order to do it, I'm just going to introduce some sort of another different abstractions, and those abstractions are built using the programming model provided by Hopac, and using which we are going to solve this problem in a concurrent fashion. So in order to do it, we are actually going to create something called a generic worker. A generic worker takes an input channel and it does not know what it has to do with the input. So it also takes another higher order function which transforms the input to the output. And once it finds out the output, it is going to put that into another channel, output channel. And we are having something called ID for the job to identify which worker is doing the particular job. And to model it, we are having something called a record type worker response, which is taking up, which is having two properties called result to represent the result of the worker, and another ID, another property called ID. That ID is representing the unique identifier of the worker. So we have something called a worker function, much like a constructor which creates the worker for us. And this worker takes three parameters. One is the ID of the worker. The second is the higher order function F, which defines what we need to do with the input and the input channel itself. Here, inside the function, we are creating an output channel for the particular worker, which is so specific to this particular worker. And we are in the next place, we are taking the value from the channel using the take function, and we are calling another function called onInput, which does when an input arrived in the channel, it does the computation, and once it computed using the higher order function, it returns the result y back to the out channel. And we are just using the job for server and the start. These are all the functions in Hopac library. Using that, we just call the functions, and it will spin up the worker. Just think of like spinning up a new thread or kind of stuff here, and that new thread is running in the background in a lighter manner, and it is receiving its input from the input channel, and it after some processing, it is returning the results to the output channel. And that is the generic worker. And this generic worker needs an input channel, and that input channel is going to be fed from the input feeder. This input feeder is again a function that takes an input channel and a list of inputs. So when it is going to traverse through the list, and for every item in the list, it is going to take that from the list and going to put that into the input channel. And this is the only thing that this input feeder does. Now we have one abstraction to process the input, and returning it after processing, it is going to return the output to the output channel. And this is on the input side, where it is going to get a list of something and going to feed it into the input channel. And there comes the business logic, which is not straightforward calculation of hash, SHA-256 from the standard system cryptography library from .NET. We are just going to open the file, get the stream out of it, and giving the stream to the SHA-256 and computing the hash. And I think you can replace that with any business logic here. Just for the demonstration, I'm just using something called compute SHA-256. Okay, so now we have all the independent pieces together. Now we are going to put the things together. So this is a function of SHA-256 of directory files, where we have list of workers, the number of workers that we want to run, and the directory path against which we want to compute the SHA-256. So here we are just we are initializing the input string, and we are getting all the file path from the directory. And once we have the directory file path, we are just feeding that as an input to the input channel. And we are just starting that so that it will be running on its own life cycle. And the second thing is, based on the worker count that we received, we are just calling the worker function and initialize all the workers. And do you remember that worker function is already returning the output channel? So after initialization, we are actually storing the worker out channels, and that based on the parameter, we can create n number of jobs. And the last thing is, we are just going to print the responses from the worker which is doing the SHA hash of the files. So once we are doing here, we are just going to choose between all those channels, and whichever comes first, we are just going to print its response. And we are going to execute the job for all the file path. And this is the results of those functions when we execute against my downloads directory. My downloads directory was pretty big, and it has something called, has some 16 to 41 GB of data of various file size. So and my configuration is right outside, right on top of the slides. So if you look at the example, the sequential one, where I run with only one worker, it gives the result after 6 minutes. And the winner here is running with worker count 4, and the response time is almost 50% lesser than the actual time which we run with respect to only one worker. So what we are actually seeing over here is, we just parameterize the concurrency, and we can do some sort of like analysis over here and figure out which one suits for this problem, and picking it and going together. So that actually comes up with the standard definition that we saw in the previous slides. Like concurrency is all about structuring the solution. What we have done here is exactly the same thing. Our problem is from the list of something we wanted to fan out, do some work. Once it is done, we want to again merge the results back, and here we are printing it. But in a real world, in the place of print, we can replace that with another set of fan out or fan in, depends on the program that you are solving. We can always do things in an individual level, and then we can put the things together, and provided if all the things goes well together, we can compose them and we can provide a stronger solution. So that summarizes the talk, and the concurrency is all about structuring the solution, and we as a functional programmer, we already doing that, and if we just doing that together, like concurrent programming becomes like functional programming is, and concurrent programming is nothing. It's like it's very natural, and it is so close to each other. Like it's just a matter of putting some some more abstraction on top of whatever we have did, and we can make things concurrent with less number of code. And my solid recommendation will always be choose the right tool for the job. So the examples that we have seen in the talk is just for communicating the idea across. And before applying the tools like Hopac or any concurrency programming model, it adds complexity to your code in one way or the other. So always think twice before applying something. If it is something which makes sense to your problem, apply it and make value out of it. And the slides and other things we have just covered the Hopac library at a very high level. We just showed the programming model and how things work together. And if you want to have a deep dive, check out my blog post on Hopac, where we are going through all the examples in details and get more meaning out of it. And as references, these are all the references. Like the Hopac documentation has a beautiful documentation on how things working together. And there are a couple of good talks by Rob Pike from Golang about how concurrency works. And the last talk is one of my favorite. Concurrency is not parallelism, is something which is mind-blowing. And that's it.
All right, Tamish, thank you very much for a great talk. Can you turn on your camera now so that we can answer some questions?
Sure.
I'll see if I can use Skype well enough to switch between the two. All right, there we have you. Cool. So we've got 5 minutes for questions. There's one question from Andre asking whether Hopac prefers a functional programming approach, and is it less favorable to do an object-oriented programming style with Hopac?
At the end of the day, Hopac operates over jobs and channels and alt. So the some of these primitives, and these primitives does not have anything specific in the functional stuff. So it's all about how do you structure the things. Yeah. So functional is something which is very natural, but there are some places, for example, if you look at my blog post, I have one example on how to implement timer in using Hopac. And that timer component is actually use some sort of object-oriented things where we wanted to track some initial internal state where object-oriented is much favorable. So it depends on the problem, but Hopac does not constrain you to use one particular way. At the end of the day, it's all your own abstraction you are going to build on top of either function or object-oriented stuff.
Yeah. So I think the summary is then sort of the functional primitives themselves in Hopac, they're functional, but then you can integrate it in any sort of application.
Exactly.
As a follow-up question, I'm betting we have some C# audience here as well. So what do you think would be the best sort of way of integrating maybe a bit of F#, a bit of C# if people want to start playing with Hopac, but do have sort of larger C# systems?
But we already have very good documentation on how to integrate F# with C#. So all we need to do is abstract that particular piece alone and put some type wrappers around it. And inside that wrappers on the F# side, we can leverage the Hopac, and we can completely shield the C# side from the Hopac references, and we can execute things inside F#. And at a micro level, depends on how we are going to slice and dice. and we can execute those things and inside that and get return the results back to the C# front.
There's one more question on Slack saying, does this Hopac stuff make sense in, for example, ASP.NET Giraffe application? So do you have any thoughts on using Hopac with Giraffe?
Giraffe, okay. Can you repeat the question again? I didn't get it properly.
So the question is, could you use Hopac with something like Giraffe for an ASP.NET application?
Yeah, we can certainly do. And at the end of the day, the Hopac library builds on top of, it has a nice integration with the task and async. So Giraffe is already built on top of task. So the task interoperates very well with Hopac. So that particular piece alone we can give task as an input, and that will give you that thing. And once the output of the Hopac library can be transferred back to the task, and we can return it back to the Giraffe, and we can integrate that with the existing ASP.NET application.
All right, so people can sort of use Hopac and then package it as async or as tasks, and
exactly.
Use that. We've got one more question. Will the slides be publicly available somewhere? We'll try to collect them. We'll have the recordings available. Tamish, are your slides going to be somewhere? I'm sure they will be.
Yeah, I will be doing that after the slide. I will be tweeting that link after that.
So follow us on Twitter. We'll tweet links to all the slides. And there's one question which is probably for myself. So is the next F# going to include live GitHub pull requests and discussion on documentation? Well, we will definitely do more comparison talks like the next one to get documentations improved. And Tamish, thank you very much for joining us.
Thank you, Thomas.
And thanks for a great talk. And we will be coming back to you in a minute with a talk from Hin talking about Giraffe, Suave, and Freya. See you in a sec.